So what I wanted to start with, you want to hit the lights? What I wanted to start with, this is, I can skip the music.
Yeah, I can turn it off.
How about if I switch over here?
What I wanted to start with, this is a video that was done by, I think it's a Norwegian photographer who went to, is it Norway or Finland? I forget.
It was Finland.
Finland, yeah. He went to the northern end of Finland, which is above the Arctic Circle, and this is just last month. And one of the things which prompted him to do this at this time was that in February there was the largest solar flare in 4 years. So he went camping for a week above the Arctic Circle and took this HD video of some of the Aurora Borealis, which are one of the most beautiful expressions of the interaction of the Earth's atmosphere with the cosmic radiation, particularly the solar energy that is hitting it continuously. So let me just play this first of all, and I've left off the soundtrack.
That's the Aurora Borealis.
Yeah. Now this, you can see it's a time lapse because you can see the stars moving. So this is faster than it would appear to you.
It's like streams of water.
You know how much faster?
Well, I don't really.
You see how fast the stars are going.
It was like a total of 77 hours.
If you didn't tell me this was somebody filming this thing, I would say this is like special effects.
Yeah, it looks like
it's amazing.
It is real special effects.
Yes,
yeah.
That's the real color.
It's special effects.
It's color you're saying that most of the time.
Yeah.
And we're going to go into in a few minutes how this works, why this happens.
So you can see you get pretty, I mean, it's a lot of green, but also red, blue, white, yellow.
Is that the moon one?
Yeah.
And this happened exactly when?
Last month.
Last month. Before the earthquake.
February 18th.
Before the.
I don't know the exact date. They just said March.
February 18th. Oh.
February was the solar flare. These videos are from sometime in March.
Oh.
That was a cloud. Wow.
This was sort of a collection. I just Googled, you know.
You got the lights again, please?
I Googled ionosphere and pulled together just a number of things about this just to explain what it is. The atmosphere tends to be divided, or at least categorized, into different layers. Most of our weather is within this small band here. You figure Mount Everest is only about 5 miles, which would be maybe 9 kilometers. So maybe that would represent Mount Everest. But already by the point, you cannot live at that altitude. When climbers who go up Mount Everest, they talk about the death zone, where even if you have oxygen, you will die within a fairly short period of time.
Well, why is that? Wait, if you have the oxygen.
Well, because the pressure on your body, people they get embolisms in their lungs, they get all kinds of, you know, these hacking coughs, and they tend to, their bodies deteriorate.
How long would it take for that? I mean, haven't people gone up there?
Oh, well, of course.
They don't stay.
They don't stay. That's my point. You go up there, you take a few pictures.
Last for a week or two, you know.
Yeah.
Barbecue hot dogs.
No one's built a hotel up there. Okay.
There's The 7-Eleven.
No.
They can call it
Donald Trump's
Club
gonna
Ed.
do it.
No. Okay, so that's, you know, that's sort of the thickest part of our atmosphere, and even before you get outside of that, it's uninhabitable without, you know, without pressure suits and things like that. What's normally considered the beginning of space is about 50 miles, which is roughly 90 kilometers. So this would normally be considered the beginning of space.
Well, 90 kilometers is down there.
No, 90 kilometers
It's that
is
arrow.
this line.
Oh, I see.
Okay.
All right.
So the stratosphere, the ozone layer, that's all within, this would be about 30 miles, 50 kilometers. 50 miles would get you into the ionosphere, which can extend much further than this, but which is defined by that part of the atmosphere which is ionized. That's where the name comes from. And what it means to be ionized is that the ultraviolet light, other kinds of radiation that are coming primarily from the sun, cause the atoms of oxygen, hydrogen, in particular, lighter molecules that can get up this high, to lose one or more electrons. So they become charged particles, which is why you get the colors. Those atoms are fluorescing much like a neon bulb or a fluorescent light. That's a plasma, which consists of charged particles which glow when, you know, when their electricity is conducted through them. So that's what describes the ionosphere, just in terms of sort of the heights involved. This, they say, is, I mean, this isn't to scale, right? That's 90 kilometers. This says, you know, 350 kilometers, which on a scale would be much higher, and it can go much higher than that. But 350 kilometers is around 200 miles. 200 miles is roughly, maybe 220 is where the International Space Station orbits. So even though we all think about, you know, it's a perfect vacuum, right? Is that the space station, every couple years, they have to boost it back up because of the drag of this, the small percentage of molecules that are still up there. And the space station, because it has these ridiculous solar panels, it has the square footage of a football field.
Yeah, really?
So, yeah.
Well, they're not ridiculous up there, though.
Huh?
I mean, you need it.
What?
You need the
Nuclear
solar
power
panels up
plant
there.
would be that.
He's talking about
Well-
the solar panels, because you said they were ridiculous. He said they're not ridiculous up there,
No, I
are
guess
they?
nuclear would be better.
It's just-
But they create an enormous amount of drags, so that they gradually get slowed down and they start to fall. So periodically they have to actually boost them up into a higher orbit. So the space station is around 220. The Hubble Space Station is about,
Kilometers or miles?
well, I'm talking miles.
Okay.
The Hubble Space Station is about 325 miles up. And the space shuttle can operate anywhere within that span. So to service the space shuttle, they had to go into a substantially higher orbit in order to link up with the Hubble. The space station is in a lower orbit.
How many miles does it take to get to the moon?
Well, that's about 250,000. Well, that's,
So the Hubble's at 300 miles? 300?
yeah, 325, something like that. So, I mean, the Hubble's orbit degrades over time as well. There's nothing empty about this region. And there's some really amazing things that happen because it is a plasma, because it's electrified. And people can print this out if they want to have a copy of it. But I just included sort of some of the key features about this. The fact that it produces a plasma so that you get ions and free electrons. And particularly in the more rarefied areas of the ionosphere, it takes a while for them to recombine. And when they're in that ionized state, they will conduct electricity.
Can I ask you a question?
Yeah.
Why did the aurora have the shape or appearance of like curtains?
Yeah. Well, I don't know the exact answer to that question, but one thing that I'll tell you is that the Earth has a magnetic field that looks sort of like that under, normal circumstances. It gets bombarded by solar radiation, which tends to distort the field and turn it into more of a teardrop.
Right.
You may have seen pictures of this.
Right.
So that the solar wind, so-called, tends to flatten this out and stretch this out. And sometimes, well, two things can happen. The charged particles from the sun can sort of spiral along these magnetic field lines, which come down at the poles, which is why you see the auroras. They usually are sort of a circle. And you can see these on Saturn as well. They've got same thing happens on Saturn, where these charged particles can come much deeper into the atmosphere following these magnetic lines of force. And when they hit the atmosphere, then they glow. So exactly why they shimmer, I mean, that would, I don't know. I don't really know the answer to that.
You can see from that why it is so dangerous that the poles are shifting, because there's a point at which the force-free part will be along the equator, and then those things would come in. All the various heavier gamma and other rays would be able to come right into the center of the Earth.
Or what? I mean, people may have seen this. There was a reference in Poulinet's interview. Yeah, when he was being asked a question about the 62 million year cycle, and he didn't answer that, but he said, well, certainly one of the things that could threaten human life is this reversal of the poles. And the poles reverse on the sun every 11 years. Every solar cycle, the entire magnetic field of the sun flips.
I have a question on that. For the way that I understood it from listening to something is that it's really the way that the everything is moving on the sun flips, the north and the south.
Uh-huh.
Is that right? That it's going from like a north-south to a south-north cycle? Or is it an actual...
Cycle of what?
Like, the thing I think about is winds, that the winds are moving from, one way on the north part and one way on the south, and then after 11 years it shifts, so they're going the other way?
That I'm not sure about. I think the sun, the sun does revolve.
Right.
And you can see sunspots. I'll show you some movies of sunspots in a little bit. And the theory that I've read about the pole reversal is that the magnetic field lines get tangled up, get twisted, and then they sort of break and flip over.
You're telling the sun now.
That's the sun.
And it's supposedly the cause are the sunspots. Because they also travel in that 11-year cycle to one pole and then the other. Is what
they do rotate. Yes, they do rotate, and they are expressions of the magnetic field lines of the sun. It's sort of where the field lines erupt through the surface is where you get these darker spots.
Right.
But you wouldn't say that the sunspots cause...
Well, that's what I'm asking, I guess.
Yeah.
It's really a question.
they may be a manifestation of that. I don't think anyone really knows what causes it.
Right.
They've observed it since about the 1750s. They noticed that there seemed to be an increase and decrease in the number of sunspots. But we'll get back to that in a while. That pole reversal does happen on the Earth. And the reason we know that is that if you look at volcanic areas, if there are magnetic or minerals that contain iron in the magma, when they cool, the iron particles will tend to be aligned with the magnetic field at that time. And particularly if you look at these mid-Atlantic ridges, right, that actually this is what really drives the tectonic plate motion that results in earthquakes like we saw in Japan, is that magma is coming up and creating, the biggest mountains in the world are underwater. Okay, there are mountains bigger than Mount Everest underwater. And that's because of volcanic activity where the magma can come up and push apart the seafloor at that point. So over time, you can see on the seafloor that the magnetic orientation of the solidified magma has reversed directions. And that can take, between tens of thousands and millions of years to occur. No one knows why or what really determines the frequency of it. The last time we had a pole reversal was about 780 million years ago. So that does happen. That does happen on the Earth.
In other words, it's late by about 550 million years.
Okay, but
They've actually started measuring the strength of our magnetic field by looking at ancient pottery, where they can date the date that the pottery was made, and they do an analysis of exactly what you're saying with the metals and the clay.
Right.
And they can tell whether it's increased or decreased, and what the rate of increase or decrease is.
Well, the thing that Poulinets in particular talks about is when you have a pole reversal, it doesn't happen like that. It could take hundreds or thousands of years for the pole to actually flip. And you can see, the North Pole is moving right now. The North Pole can move like miles in a day. And it's not as simple as just saying, well, the way it's always described is you have it's like a bar magnet with the North and South Pole. There can be sort of subsidiary poles.
There's a magnetic pole as well as a...
Well, that's another question.
Magnetic north
you
is
can
not
you
a
can
pole.
have
Right.
you can have a magnetic pole as well as the physical pole of rotation.
Right.
But aside from that, you can have multiple north poles. You can have sort of weak areas of north polarity and south polarity. And all over the Earth, depending on sort of the geology of the area you're in, you get distortions of sort of the general magnetic field line. So you can get maps that basically pilots have to use this. Because if you're simply using a compass to tell you what north is, if there's a big mountain over here with lots of iron ore in it, it's going to deflect your compass.
But it is, the North Pole is the magnetic North Pole, right?
Well, but I'm saying it's not that simple.
I know that it shifts, but somebody said something.
The magnetic north, if you use a field map, you have to take into account that when you put a map on a field map, that you're not looking at, they give you a number of degrees that you have to take into account that's away from what would be the true North Pole.
So
Magnetic north and the true
if
north
you
are
traveled
several
over the
degrees.
surface of the Earth, north might wander around. And at every point, it's telling you this is north. So the magnetic field is much more complex than just saying, well, this is north and that's south. Presumably because the Earth's core is molten, although again, that's one of those things, this is all theory.
Just an assumption.
Well,
And there's a lot we don't know about that.
But I have a question about that, because I wonder why there's always this proviso that says we don't know. Isn't it an obvious assumption that if you have magma and lava, that if you have further into the core, you're going to have a liquid?
Yeah. Well,
why is that always? Why do people always say, "Well, we don't know, we don't know"?
Well, I mean, it's any hypothesis. It's better than the old hypothesis that we had that the Earth was sitting on a turtle, right? But it probably isn't the whole truth.
Yeah, we've been down about 2 miles, right? And this thing's 25,000 miles down.
Yeah. So
12,000.
I mean, obviously volcanism is a good reason to think that it's molten. You know, and there are earthquakes actually tell you a lot about the interior of the Earth, because the shock waves go down and can be reflected and recorded on the other side, or 1,000 miles away. So the way that the seismic waves travel through the Earth can tell you quite a bit about what's inside. But it's theories which always change, are always overthrown and replaced by better ones. So
also to say, I mean, they also say that part of the reason we have a magnetic field is that the center is an iron ball and all this other stuff floats on top of it, and that you have a separate rotation, and that's what you get your magnetic, field. So, but this is stuff you don't know. Nobody knows.
I mean, Mars does not appear to have any significant magnetic field. It may have in the past, but that's an important problem. We've talked about this whole question of not only trying to provide an environment for astronauts that includes gravity, or something that can have the effect of gravity in terms of preserving bone mass and things like that, but the whole electromagnetic environment, right? In the extended sensorium, they wrote about how people's sense of time, how a 24-hour day can become a 50-hour day simply because you have no outside electromagnetic field. I mean, that's pretty astounding. Yeah. That regardless of you're inside an enclosed building or underground or something, and there's no sense of day or night, but if there's any kind of electromagnetic radiation that gets in there, the body maintains its normal 24 or 25-hour cycle of day and night. But if you block out that component, in some of these cases, people flipped into a 50-hour cycle, and instead of sleeping 8 hours, they'd sleep 16, and they'd still have the same number of meals a day. It's just on a 50-hour basis. So in terms of space travel, the existence of a magnetic field, in terms of how that shields us against all this radiation, is an important factor. What direct effects does the magnetic field have on the human body? We don't really know. But all of those things now have to be taken into consideration.
And Tony, you saw Sky made the point that we have no idea what the Earth is composed of. This is a standard hypothesis, but there's nothing obvious that there's going to be a flow of magnetic molten metals, and that causes what are the electrical currents that define the inside of the Earth? What are the other rays connected to the electromagnetic spectrum? And then Sky makes the point that the level of science, the research that's done to figure out what causes the Earth's magnetism is not done. He said we've done about as much science as going to the level of the skin inside your head.
Yeah, right.
So you have to live with the fact that these are all unknowns, and the whole question of the relationship between magnetism, electricity, light, non-visible light, these are all themselves working hypotheses. And this is what Einstein was working on at the end of his life, his hypothesis was that there was a universal set of physical principles in which light, magnetism, electricity were all aspects of the same process. How does that work? We don't know.
I mean, if you think about some of the material that's been in the briefing about this guy Geller, who just emphatically states earthquakes can't be predicted because you really get a sense of this whole question about the tyranny of the senses, right? He's saying, well, we can feel the earth move, right? Buildings fall over. That's real. Everything else is just, rubbish. And that it's very much that. I was thinking earlier, I'll show you some of these movies. We got to keep moving here. But we take certain things for granted. Oh yeah, well we have radio telescopes that listen to radiation in that waveband, and we have infrared telescopes and ultraviolet and X-ray. Well, none of those things can be directly perceived by us, so how did we figure out there was anything there to measure? Typically it's anomalies in things that we already could measure, where we had an idea there must be something else there, and then had to figure out, well, if there were something there, how would I develop some technology that could measure it, since my instruments can't? So all of these things are trying to, see the unseen and try to interpret what that is telling us about what's actually occurring as a real physical process. So just in terms of the ionosphere, that it breaks apart molecules. It's crucial for radio communication because you create a completely different, the atmosphere doesn't just become thinner and thinner. The fact that it is ionized and can conduct electricity, and remember, a moving electrical current produces a magnetic field. This was something that Sky had done a thing on in terms of the oceans.
Oh yeah.
Right? That the flow of water in the oceans, or and the biological life in it, creates sort of this series of magnetic fields and electrical currents and magnetic fields and electrical currents. And as we'll see, this is far more important than you ever imagined. And that there is a direct interaction of all of these things in a very dynamic way. This just describes the different layers. Ultraviolet, X-ray, shorter wavelengths of solar radiation are ionizing. They have sufficient energy to dislodge an electron from a neutral gas atom or molecule. And then over time that they will recombine. There are changes between day and night, right? Obviously at night you don't have any solar radiation directly hitting the atmosphere, so that you'll have a decrease in sort of the thickness of the ionosphere. There are also changes during different times of the year. The sunspot cycle, these are indicators of the activity, the intensity of the activity going on the sun that would be reaching the Earth. And some of them are rather spectacular. Now this is a little more technical, but I at least wanted to include it to get a sense of how big an impact this has on climate and other phenomena. Now, I think thermospheric neutral winds, I think that means heat-driven winds of neutral atoms and molecules. Okay, that would be sort of the lower non-ionized part of the atmosphere. So you can have these neutral winds which wind up moving the ionized particles in the ionosphere across the geomagnetic field lines of the Earth. So you have charged particles being moved across magnetic field lines, which drives what they call an atmospheric dynamo and an electrojet, a powerful eastward current that flows. The E region as part of the ionosphere. They divide it up into different layers. Then on the other hand, in the polar regions, the ions in the ionosphere, right up higher, in response to the imposed magnetospheric convection electric field, drag the neutral atoms in the deeper atmosphere and can generate neutral winds with speed sometimes exceeding, that's about 2,100 miles an hour, in the high latitude F region of the thermosphere, which is somewhere in the middle of all this. Okay.
That's interesting. That's in the Arctic.
What?
That's in the polar.
Yeah, the polar regions. Yeah. Okay. The ionosphere also interacts strongly with the magnetosphere, which is this larger sort of sphere of influence of the Earth, the Earth's magnetic field that extends far beyond the atmosphere. There's a coupling between these electric currents flowing along the magnetic field lines that I drew over here that connect the ionosphere to this broader magnetosphere. So there's an exchange of ions that goes both ways. You can have, the field line currents are auroral, right? What we just looked at. Electrons that are responsible for the aurora precipitating downward along these field lines. And you can also have electrons produced in the ionosphere which flow out into the magnetosphere. Okay? The former, meaning these electrons that are precipitating down into the atmosphere, deposit a substantial amount of energy into the upper atmosphere with profound effects on both the ionosphere and the neutral thermosphere, the deeper atmosphere. They enhance the plasma density, supply as much as 1 trillion watts of heat to the upper atmosphere, dramatically altering global thermospheric wind patterns at times of strong geomagnetic activity. So this has, okay, that's it. So this has a direct effect on climate.
Like if it's not there, we're dead. I mean,
Well,
you do get this impression. It is a protection that we don't ever even think about.
It's a rough neighborhood out there.
Yeah.
It's definitely a rough neighborhood. So the atmosphere itself, provides a lot of protection,
Right.
but it's magnetic, electrical, all of these things combined. Okay, so let's see. Okay, so I can close that. All right, now I think we want to
Let's go to the NASA film.
Yeah, let me go to the NASA film.
It's on a different
Oh yeah, let's see here. Okay, now this is a little movie produced by NASA.
So pay close attention.
So wake up.
I didn't turn up the volume anymore.
Between the Earth and the Sun, we tend to imagine empty space. But every day, every moment, solar forces fill the void and interact with our planet. The gray mesh you see here is the magnetosphere. It's effectively a bubble around the Earth, created by our planet's magnetic field, squashed and elongated as intensely energized solar particles collide with it. Without the magnetosphere, life on Earth would likely cease. Naturally, we want to know more about it, so let's start close to home. These near-Earth satellites monitor solar activity. interactions with our planet's atmosphere, and other aspects of the Sun's condition. You'll notice how they orbit the Earth quickly, about once every 90 minutes or so. Remember this because the rate of time's passage will change as we move through the solar system. Further away, we see satellites measuring the three-dimensional boundaries of the magnetosphere as it interacts with the solar wind. And let's be clear, this is more than an academic exercise. NASA's fleet of research satellites gathers vital information. Solar phenomena can jeopardize astronauts and provoke dramatic challenges to communications systems and the electrical grid on the ground. Time speeds up as we move out. More space between objects means we have to travel greater distances, and our tour of the heliosphere only lasts a few minutes. While we're traveling, take note of something you might not have considered before. Not all orbits look the same. In close, satellite paths essentially circle the Earth. But farther away, we begin to encounter a wider variety of orbits, designed for varying purposes. The cluster vehicles are on a high elliptical flight path. Geotail makes a lazy loop all alone. The two stereo satellites fly in relatively close formation, but they won't stay that way for long. I'll show you how in a moment, but the point is, navigation out here is harder than it looks. A vehicle can't simply fly from place to place, but for some missions, like stereo, precise position makes all the difference. Why? The two stereo satellites will deliver 3D pictures of the Sun, similar to the way your two eyes perceive 3D. Remember I said to keep an eye on stereo's flight path? Watch as one of the two stereo vehicles intercepts the Moon's orbit a second time. Here it comes. As they close the distance, the spacecraft uses the Moon's gravity to execute a cool maneuver, like a roller coaster zooming up and into a corkscrew just after hitting a big drop. Now the vehicles are headed to their final orbits. Tight loops around the Earth, loose orbits out into space, bank shots off the Moon. There are many ways to travel from place to place. But sometimes travel is not the goal. Sometimes it pays to park. Welcome to a Lagrange point. This one, L1 in space speak, denotes a relative position between the Earth and the Sun, where the gravitational pull of each object is in approximate balance. These so-called halo orbits around L1 make good places for hovering spacecraft to take observations of either the Earth or Sun. We find a number of observatories patrolling out here, including an extremely famous and extremely successful solar observatory called SOHO. Notice how L1 exists well in front of the magnetosphere. This part of the solar system is fully bathed in the solar wind, without the protection of Earth's magnetic shield. Therefore, it's extremely useful for studying solar activity without interference from the Earth. Let's briefly revisit the area around the Earth. Simulated time slows again as the distance between objects shrinks. But as we once again approach our home, you'll notice the calendar has advanced 2 years. New satellites have entered the dance, including the 5 Themis vehicles. The near-Earth fleet of satellites swarms like bees around a hive, some ranging out beyond the magnetosphere, some well inside. It's provocative to consider that all this activity takes place in space, something we generally perceive as empty. But what we find instead, from light to charged particles to magnetic fields, demonstrates a strange and wonderful solar vitality. In fact, there's a particular scientific discipline that describes the study of these things. It's heliophysics, from the Greek word for sun combined with the word used to describe the study of matter and energy. Heliophysics studies how the sun's sphere of influence interacts with planets and the interstellar medium, the barely tangible stuff that fills what we typically regard as empty space. Almost done, but we've got to get moving if we're going to see the full extent of the sun's influence. Pulling way, way back, Earth's magnetosphere effectively disappears. Almost all of our solar observing fleet shrinks like boats on the horizon. Almost, but not all. 2 legendary spacecraft, Voyager 1 and 2, are out there, still taking measurements. Notice the gravity assist bank shots in their flight paths. Launched in 1977, the Voyager spacecraft are the most distant artifacts humanity has ever cast out into space. Time capsules from a small blue planet. They are also the first human objects to encounter the sun's termination shock, the area where the solar wind slows down enough to be affected by the flow of interstellar particles. In a couple of decades, one of the Voyager crafts should pass the heliopause, the zone where the sun's influence meets the interstellar medium. Years later, it should encounter the so-called bow shock. That's the wake in flowing interstellar particles as they move around the bubble of energy and particles emanating from our star. Our star, the sun, neither particularly large nor powerful as stars go, stretches itself out further than even our most distant probes. As we discover how to coexist with our own solar dynamo, we stretch our ingenuity and imagination to meet its grand reach.
And a little Mozart.
It's unbelievable.
Bravo, bravo. Okay. So I don't know, I mean, hopefully people got some, I mean, I was totally blown away by how many satellites are already out there. I assume that these are actually still up there, or were up there when this was produced.
Are those just the American satellites, or because the Europeans and the India and so on?
I would assume it's all of them.
I think that's just our Heliophysics satellites.
Oh yeah.
Those are not other satellites that we have.
Oh sure. Yes.
Space
But-
traffic is becoming a problem with the orbits.
Yeah. But you get a sense both the magnetosphere, how this interacts with the sun, and that the sun itself also has its own magnetosphere, which we will get to. We'll get to in a minute. Now, oh, I know one thing I wanted to show you. This is a snapshot from, this was while you were sleeping from Friday, which Michelle Fuchs did, and part of it was on the Poulinet's interview. And this just shows some of the kinds of effects. This deals with the earthquake precursors, but many of them are related to the ionosphere and how various phenomena can be recorded and used to gain insights into this whole issue of earthquakes. Well, let me just see. Let's see. Oh, one of the things, the ionosphere, this would be the ionosphere where you see these electron symbols, that during an earthquake, the level of the ionosphere actually drops. Various kinds of radiation, VHF, UHF, the signals, they become stronger or weaker as the ionosphere drops. I had mentioned in that little article about radio propagation. You can have charge accumulation on rock outcroppings. Some of these, this is GOES, that's one of the satellites that we've cited. That when these positive charges, after you've ionized the air, they will recombine. The positive and negative charges will recombine. When they do, they release infrared light. So you can measure changes in the rates of these kind of phenomena in the ionosphere. Air conductivity sensors detect charges that can cause lights in the sky. This is Demeter. Sense extremely low frequency magnetic disturbances. Magnetometers detect ultra low frequency and extremely low frequency changes in the magnetic field. Radar can measure the height of the ionosphere because it reflects off of it. And the GPS signals, right, your location is determined by the different length of time that it takes for a signal to reach you from 2 or 3 different satellites in the sky. So that's how you measure your little GPS on your dashboard is measuring the difference in distance from satellites based on differences in time that signals take to get to you. So that's how it determines where your location is. And you would typically need at least 3 to form, to triangulate your position. Well, changes in the ionosphere will tend to throw them out of sync. It will change their relative phase. And so it both has to be, measured to make the GPS work accurately, and the GPS, used for other reasons, can be used to measure these kind of changes in the ionosphere. And then we have snakes and frogs down here. the biological detector system. So that's just some of the things which Poulinets and others are looking at to try to...
They don't have destiny up there.
It doesn't exist.
Yeah, it doesn't exist. Okay, now we did sentinels. Okay, so now, let's see, I can get rid of that. Okay, now let me go to the NASA website. Come on up. Okay. Let's see. I think I had, yeah, here we go. One of the satellites that was shown in the movie was SOHO, which is, I don't know, Solar and Heliospheric Observatory. Now, these are sunspots. Which basically are rotating with the sun. They appear dark because they're slightly cooler than the surrounding surface of the sun. And sunspots have been observed as long as there have been telescopes. It was only in the 1750s that people counted sunspots and noticed that there was a change in the number of sunspots from year to year. This is a different satellite, but it's looking at the sun from 1996 to 2005. And the last solar cycle, they're normally 11 years from maximum to maximum. The last one, the minimum was in 97, went to a maximum of 2001. So this one is basically going to go from a minimum to almost to another minimum. So you'll see the activity, let's see.
Question is, what causes the sun to heat up?
Well, that's fusion.
Yeah.
Okay, now this, I think, yeah, see it has the years. And you look here, you can see these loops.
Yeah.
Those are, magnetic fields. 99, 2001, I think I said was the maximum.
Yeah.
Now, I'm not sure the frequency that they're measuring this at.
That's a solar maximum?
Yeah, 2000,
In the
yeah.
bottom right, there's a huge CME at the bottom.
So this is going just past,
Another one on the left.
yeah, let me,
Wow.
I'll run this one again. Now you'll see it's going to start, see now it looks quieter. Okay, let me do that one again. And you can,
What was the platform that they took these, was this satellite on Earth? It was
SOHO.
no, this one, no, this is a different one. it's called ELF, I think. I don't know what it is, but it's
says
not.
Soho at the top.
Well, that's where the movies come from.
Oh, I see.
But this one, I don't know. I don't know. Okay. So 95 was the minimum. So this is a relatively quiet beginning.
My question is, what causes the sun to heat up from what it normally is to becoming hotter?
No one knows.
So it's got to be intergalactic
Well,
activities.
I don't know. Yeah, you can see down on the left there, there's,
And on the right.
yeah.
And how long have these 11-year cycles been going on that we know of?
Well, they have been monitored since the 1750s. So we've begun, I think, cycle 25.
Right.
It's only been, they've been keeping track of them. They normally are 11 years in length. I have a diagram that shows the start of the current one. Okay, now this is a nice one. Now this starts in visible light with some kind of filter, so you can see the sunspot motion. And then they look at it in different frequencies. This is 2000, which would be getting near the maximum. This is another frequency. I can't tell you what. Yeah, now if you noticed, I'll play this one again. The red circle is to blot out the actual surface of the sun so it doesn't overload the sensors. And the little white circle shows you what the actual diameter of the sun is. Okay? So these are showing you, why is it? It looks pretty quiet, right? Pretty quiet, a few dots on it.
That looks a little hotter.
Yeah. You can see those would be called solar prominences or solar flares.
I think that one's the most interesting.
And the static, you just saw that static on the screen?
Yeah.
That's the charged particles, basically scrambling the detector. That's what all that static is on there. And look at how it's sort of explosive. You can have 1 billion tons of charged particles thrown out from the sun in any one of those.
Is that what's called solar wind?
Or, well, all of this would generally be called solar wind. These would be called either solar flares or coronal mass ejections are the really big ones, where you can have these huge clouds of charged particles that can, if they're pointed directly at the Earth, they can knock out satellites. They can cause power outages on the ground.
Like you don't want to be standing there.
Well, there was an article in Sky and Telescope which said there's going to be a big solar storm in 2013.
Uh-huh.
And they said that there occurred one in 1859, I think it was.
Right.
Well, I guess people have heard about it. They knocked out the telegraph lines.
Yeah.
They did what?
This new one coming up
That's
is
the telegraph lines.
it's going to, knock out the communication.
To some degree, satellites, they can try to harden them so that critical electronics are shielded to some degree from this. But
Well, you see all this stuff spewing out, but they're also, since there's such a massive gravitational pull, it's probably also pulling in particles of all sorts, and even matter of some sort.
Yep. Now this is just labeled spectacular coronal mass ejections. Again, this is the diameter of the sun, but all that static is caused by the charged particles that are hitting the satellite. And you can see this is occurring over the span of, of a few days.
Where is it?
That was a big one.
What's the thing covering it?
Well, it's covering
It's just a
It's to
shield.
prevent, that would tend to blot out the picture.
Right, because it's so bright.
The white circle is the actual.
That's a
Is
UFO.
the sun.
That's
Notice he's not affected at all.
It's a chemtrail.
It's a chemtrail.
Not affected at all by the sun.
I know, I thought he was going to
Okay.
get blown away there.
Do we
So-
know where we are in the age of the sun? How old is our?
about halfway.
About halfway?
Yeah.
4 billion or something.
Yeah,
they
I
say.
think it's about 5 billion. I read something in investigating this stuff about our position in the galaxy, and I don't know whether this is true, but someone was saying that they did not think that our sun originally came from this
Our
galaxy.
Oh my goodness.
That around our galaxy, they're sometimes called dwarf galaxies, little clusters of stars that tend to get absorbed by the bigger galaxies. And so this guy was positing that our sun came from one of these dwarf galaxies that got absorbed into the Milky Way. And that certainly could account for the motion of our sun apart from that of the galaxy, which we'll get to in terms of the 62 million year cycle.
You mean the up and down through the galaxy?
Huh?
The up and down
Yeah.
motion through the
Bob's
galaxy?
up and down.
Yeah. Okay, so I'm going to stop with those pictures. 7:30 already. Okay. Now, in terms of our galaxy, I got another video. I'm going to show part of this. This is another one, the same photographer made, called The Mountain, which he went to Spain. This apparently was also last month. He went to Spain, climbed the highest mountain in Spain, which is about 11,000 feet, which is, a little over 2 miles above sea level. So there's an observatory up there because it puts you above at least a significant part of the atmosphere. I particularly wanted to show this for some of the scenes of the Milky Way. Let's see. So that's the moon going down. That's Orion over there, the belt of Orion. So you can see you're above a lot of the clouds.
That's incredible.
Wow.
I know.
And this would be above the tree line. So there aren't any trees up here. Okay, now.
This was through a sandstorm.
Yeah.
Yeah.
This is Spain, so there was a sandstorm in the Sahara, which blew across the Mediterranean, so this is all sand here. This is the plane of our galaxy. That would be looking toward the center of our galaxy. And the word galaxy comes from the Greek for milk. So the word galaxy literally means Milky Way. I'll just let it get a little higher up. But this is basically looing in toward the center of our galaxy, and these darker areas are dust. So one of the problems of trying to understand the structure of our galaxy is that all of this dust tends to blot out everything behind it. And if we get to it, I have a couple still pictures of galaxies that are taken in infrared. Infrared, which is heat, essentially, tends to pass through dust clouds much better than visible light. So we can get, you know, somewhat better picture of that.
And what are the dust clouds?
Space dust.
They're dust.
Just dust?
Just dust.
Like asteroid dust?
We need a big
Sweep it
can
away.
of
Yeah.
Murphy's oil spray.
So it's blowing up from Africa.
No. That's that right
No,
there.
that- yeah, that's the,
That's the dust from the. But he's talking about dust in space. This is
This is
amazing.
beautiful. This is just beautiful.
It's amazing.
A nice seaside location. Okay, now this is another picture. To your question, Bob, any of the, again, that's the plane of the galaxy. Any of these black areas, it's not because they're empty, it's because they're loaded with dust. So you can't see what's behind it.
Oh.
Now that must be some kind of a filter. I don't, that's more or less the same shot. But
Yeah, but so that's the infrared, which you can see through the dust.
no. Okay,
This is
now
the
that,
color filter.
then I'm going to skip some of the trees and flowers.
That would be a trick, huh?
That would be.
Ooh.
Good one. All right.
I went up to northern Pennsylvania where Ryan and I stayed with a contact.
Uh-huh.
I think it was probably the first time we went out at like 12 midnight and looked up and you could see this splash of this Milky
Yeah.
Way. It's something that I can't remember. You don't see it in the city areas.
Because there's too much
no.
light.
You never see it. You got to be way out in the country.
Yeah.
Naturally, there's not a bunch of lights.
Okay.
What?
Greenspan is what
This is covering more than one cycle. You can see this was, we had looked at the period, one of the movies was from basically 95 to 2005, thereabouts. This is about 97 to, you would normally expect it to be to 2008, which would be 6, 7, 8. That is where you would expect the minimum if it followed an 11-year pattern. This got stretched out by about 2 years, and now we're on this side where the intensity is increasing again. So we expect, and there have been, let's see. Well, I'll just show you. This is a picture. This is 3 different solar cycles, and the only thing I'll just point out, there's sort of different aspects to it. The blue is the sunspot, the number of sunspots. The number of solar flares is green, so they more or less follow a pattern, although they're different phenomena. So you do get, this has something to do with radio waves, and the actual, I don't know exactly how they measure the, I guess that's the visible light output.
The irradiance.
Yeah.
Hmm. Who would have thought?
So there are different aspects of this which all tend generally to follow this 11-year cycle. Now, one other thing I wanted to, let's see. Well, this is in X-rays. And during the minimum over here on the right, the sun appears black because there's virtually no X-rays being emitted. At the solar maximum, it's, you know, really going.
I wonder how the hell they did that.
Now, let's see. There was all of the data going back to 1600, when the telescope was invented, when sunspots were first observed, of the intensity of the sunspot. You can see 1750s is when they started keeping track, you know, deliberately keeping track of the number of sunspots that they could identify. During the second half of the 17th century, this Maunder minimum, there was virtually no solar flares for a period of 50 years. For reasons no one knows. That was sort of a little ice age. The Thames froze over, things like that. And so this is not, it's not uniform.
1650,
Right? Over there in the red. So that you have differences. This, I'm not sure if this is the number of sunspots. I assume that's what it is over here. I don't know exactly what the black line is, but I think you get the idea that there is substantial variation in these cycles, which can have tremendous impact on the Earth. Okay, now, that's just another picture of sunspots. This, the NASA movie pretty much described this, but the sun is at the center. This would be considered, this whole thing would be considered the heliosphere, which looks a lot like the Earth's magnetosphere, with this being interstellar space, right? This is the gas, energy, radiation, whatever, that lies outside of the bubble created by the sun's magnetic field and the particles that it's blowing out. So the Voyagers, which went up in, 79, have been traveling out of the solar system for over 30 years now. And they are just passing the barrier of what they call the termination shock. I don't know exactly how they divide these areas up, but if they continue to operate, that they will actually pass completely outside of our sun's range of influence, and will begin to sample the energy of charged particles, see what's out there. This is called a bow shock. I just found a couple days ago, I found this NASA picture, which is just gorgeous. This is a bow shock. This is an individual star that is colliding into all of this surrounding gas and dust. And because of the bubble that surrounds it, it's forming this bow shock and also lighting it up so that we can see it.
That'd make a great poster for the field.
Isn't that something?
Explain this.
Not a flash.
Yeah.
Okay, now, let's see what else we've got
So the
here.
bow shock,
Yeah?
that obviously that's ring around the sun is not symmetrical. So is that the direction the sun is going
Yeah,
in the,
yeah.
Galaxy?
Presumably that star is moving in that direction, or that's the opposite direction is where this gas and dust is coming from.
I'm saying our batch, the one for the sun.
Yeah, well, I'm saying it can be a combination of two things. I don't know what the dust and gas is, where it's moving around that star. But presumably that star is moving in that direction. That would be my guess. Okay, well this is basically it's sort of, the bottom half is a blow up of the little rectangle up top, looking toward the central region of our Milky Way. That's where we think the center is. And our current theory of the structure of our solar system is that it's basically a spiral. This is new. They did not, there are kinds of galaxies called barred spirals, which have basically a straight bar in the middle and then arms coming off from that. There are some that have a bar and just two arms that come off. Some have no bar and it's just a spiral. Some of them, I'll show you a few different pictures of galaxies if we have time. But I don't know if that, maybe that's supposed to, I don't know. It says sun's orbit. Oh, this says solar system. So I guess that's supposed to be where we are now. Does that look right? Yeah, that could be right. The Milky Way as a whole, this is about 100,000 light years in diameter. We're roughly 26,000 light years from the center. So we're sort of 2/3 of the way out from the center. There are probably about 100 billion stars in our galaxy. And up until the 1920s, the prevailing scientific view was that everything that we saw in the entire, that the universe consisted of our galaxy. And that anything that we saw was somewhere inside this. And
Up until when?
the 1920s.
Oh my God.
Edwin Hubble,
Yeah.
right, that they named the telescope after, was looking at the Andromeda galaxy, and he was, I won't go into the detail, but there's certain kinds of stars called Cepheid Variables that their light goes up and down, and that the belief is that the period of that variation is a function of their absolute brightness. So they call them standard candles. Because if you're looking at something that is, way out there, how do you know what's the distance? This particular type of variable star became used as, they called it a standard candle. That its you could determine what its actual luminosity was, and therefore, if it looks this bright to me, it must be that far away. So based on that, he concluded that the Andromeda galaxy was now, they say it's something like 2.2 million light years away, and that it is not a little clump of stars somewhere in our galaxy, but it's an entirely different galaxy much further out. So if this is 100,000 light years, about 20 times that distance would be where the Andromeda galaxy is, which may have 1 trillion stars. It's even bigger than ours. And there's probably 100 billion galaxies in the universe. That's the current estimate.
How do you make that kind of?
I know.
Well, one of the ways they do it, and I don't have a picture of this, is one of the things that Hubble did was they picked the most empty place in the sky that they could find, where there was absolutely nothing. They looked on all the existing star charts and said, we want a place where there's absolutely nothing there. And they picked a spot about the size of a grain of sand held at arm's length and stared at that spot for 1,000,000 seconds. And in the picture they took, they found 3,000 galaxies.
This is when the time of Hubble.
What?
You're saying this is the Hubble telescope?
Yeah. It's called the Hubble Ultra Deep Field.
Isn't there one that's now more powerful? I think the digital
Chandra.
Sloan something or other.
Chandra?
Well, there. I mean,
There's a
Digital Sloan Survey. That's a survey of the sky. There's lots of things going on. They're proposing to put up the Webb telescope. The Chandra is X-ray. So there are many telescopes on the ground which can take pictures almost as good as Hubble, because they can correct for the atmospheric distortion. So there's a lot going on. But the thing I wanted to, just to focus on this question of sort of where are we? Okay. This picture also, this is from NASA, attempts to show where the our solar system is in the galaxy. And two things.
This, of course, this is a computer simulation. This is a computer-generated image.
This is not somebody's taking a
This is
picture.
not a photograph.
Right.
No?
Right.
We're out a little further.
Okay. Is the galaxy as a whole is rotating. And it rotates about once every 226 million years. There is a sort of fluctuation to the motion of our sun, certainly. I would imagine probably for all of these, since they're all interacting with each other. One of the things that I was fascinated to read about when I looked into this is that apparently there's some kind of a little bubble of gas that we're now starting to plow into. So in terms of this heliosphere, the bow shock, all of this, these are, you know, real things happening right now. And that a lot of these speeds, I mean, these are relatively small, but let's see.
Is there kilometer per second?
Yeah. This is what we believe is the cause of this 62 million year cycle. The Milky Way is 100,000 light years in diameter. Its thickness is maybe 1,000 light years. The closest star to us is about 4.4 light years. Okay, so if you look up and down from the plane, the sky will be, you know, a lot less dense than if you look into the plane. This is the presumed sort of wave motion of our star relative to the plane of the galaxy, and that the length of these waves is 62 to 65 million years. And the idea is that in the same way that an individual star, through its own energetic activity, magnetic field, creates a certain bubble around it which interacts with the interstellar gas, is that the galaxy as a whole would have something like that as well. So the idea is that when you go outside the plane of the galaxy, you're in, you know, that's rural America, right? That's when you get out into it's at least less dense. This, as far as I could determine, is maybe tens of light years in distance. So compared to 1,000 light years, let's say that's the thickness, it's not like you're completely out in, you know, no man's land, but it's going to be less dense, which means that you are more subject to the intergalactic forces. Okay? Now, And as far as I can determine, we're on the upswing onto what would be considered the north side of the galaxy up here. So it may be 10 or 12 million years before we get up to the top, when presumably that radiation would be most severe. Now, the galaxy itself is moving. In fact, we'd really better get on the stick, because in about 3 billion years, we're going to collide with the Andromeda galaxy.
3 billion years.
With the Andromeda galaxy?
With the Andromeda galaxy. That's in our local group of galaxies, right? That's a mere 2.2 million light years away. And we're moving toward it at about 1/10 of 1% of the speed of light.
That would be a spectacular crash.
Okay? Although we might not notice it, because the stars are still very far apart. I mean, they have these computer simulations of galaxies colliding, and stars get thrown all over the place, but they don't sort of come together with a bang like that.
How about the gravitational pull of such a thing? Because
Well,
I understand it pulls off arms of spiral galaxies, and then a fusion of two galaxies often results in a what is called it's not a spiral, it's an oval.
yeah,
Get the name.
elliptical.
Yes.
Yeah. I don't know
So
what I
okay.
have. No, I
What's
don't
the
know.
relationship between a light year and a calendar year?
Well, a
It's
light
light
year is a
years.
distance.
I know, it's just.
How far
It's
But
not
you
a
were-
go in
When you say it's
186,000 miles per second.
186,000 miles a second for 1 year.
Yeah,
How
that's
about
like
The
6
distance-
trillion.
light to travel in?
Now, I don't know if we can't.
Yeah,
this
yeah.
doesn't really
In terms
work.
of, talking about however many
I can't-
billion
I
years
can't-
Oh,
you said
yeah.
it's gonna
Yeah.
happen, this collision.
Well, I don't know if you can really see this, but
You can go a little bigger.
I can't really slide it around. This just shows the local group of galaxies, many of which are these little ones, right? Andromeda is the biggest one in our neighborhood.
Can you see that with the naked eye?
Yes.
Yes.
Yeah.
That's the most distant object visible to the naked eye. 2.2 million light years away.
Is it in a constellation?
Andromeda.
Of course.
So I can't
The bottom
slide
corner
this.
by the lower left star.
I can't slide this thing around, but it just shows that's the Virgo supercluster, which is, you can have clusters of galaxies, you can have clusters of clusters. There are structures on the largest scales that you can think of. It's almost 8 o'clock. Okay, so, the other thing which I don't know too much about, there's this theory that there's a 62 million year cycle of extinctions was developed around 2005, and they didn't really know what to make of it. And in a year or two later, someone else came up with this idea that it was the motion of the sun above and below the plane, and that because our galaxy is being drawn toward this Virgo cluster of galaxies at about 300 kilometers per second, which is about 200 miles a second, which is where I came up with this, a 1/10 of 1% of the speed of light. That's
Right.
not too shabby. Is that the whole galaxy would create a bow shock. And that's why the top side of the galaxy is a more dangerous place to be than the bottom side.
Don't get it.
Even the
Because
bow
that's the
shock
part,
area.
that's the direction it's going.
Yeah.
Oh, I see.
If
I
the
see.
whole galaxy is moving in this direction,
Got it, okay.
this is the area that's going to be crashing at 200 miles a second
Right.
into whatever's here.
Uh-huh.
And the further you're removed from sort of the shielding effect of the plane, the more intense that radiation is going to be.
So
There's
where-
the
62 million is where's the last 62 million? Down to that.
I mean, there's-
now, one thing that I'm not clear about, according to what I think 3 million years ago would probably be somewhere in the plane, so 65 million years ago would also be somewhere near the plane.
Well, that's the mass extinction of the dinosaurs.
Yeah, so it's not clear to me, I mean, number one, it's not clear to me that that was caused by this effect. The fact that there's a 62 million year cycle over about, I think, over like 9 of those cycles, right? The papers, they talk about a 542 million year period of time that they were studying, and found that there seemed to be this pattern every 62, 65 million years.
And the rotation of the sun around the center is how?
Well, that's not clear to me. They talk about this 140 million year cycle, but the entire galaxy is rotating. That takes something like 227 million years for the whole thing to rotate once. The motion of our sun, sort of independent of that motion, that's not clear to me. They talk about 140 million years, that it may be the motion through one of the spiral arms. Oh yeah, that's what I wanted.
Okay. You gotta click on it in the lower left.
Huh?
If you're clicking on the center, you need to click down there, yeah.
That you can see if the sun's orbit were circular, there are going to be places where it goes through one of the spiral arms. So there are also going to be places where it's in between arms. So even though it's in the plane, it's going to be in a relatively empty area, as opposed to here, where it's going through a denser one of the arms.
But there are clearly areas that don't move. That's why you have the spiral arms.
Well, I think that's probably a relative term. And it's not clear to me that exactly what the sun's sort of independent motion is. The whole galaxy does rotate, but every star does have they call it its proper motion, which is why over time the constellations change shape.
Right.
Because the stars are all at different distances, they're moving in different directions.
And how long does it take?
Well,
say over time?
I mean, like the Big Dipper, in a few thousand years, it'll look substantially different, like a frying pan, where the pitcher sort of opens up and the handle gets more bent because the stars are moving in different directions. So those kind of changes can occur, in a few thousand years.
Well, I call it the Brita water filter.